previous lecture, we had developed the algebra relating to the Bra and Ket notation, and we had also considered linear operators and defined the adjoint of a linear operator. For example, if we consider the linear operator alpha, then its adjoint is denoted by alpha bar, and if alpha bar is equal to alpha, and that means that alpha bar ket A bra A is equal to alpha bra A alpha A. If this is valid, then alpha bar is equal to alpha, and we say that the operator is a real operator or a self adjoint operator. Then we said that if I consider the eigenvalue equation alpha ket A n is equal to A n ket A n, then in this is a number alpha operating on a ket, which is by definition a non-null ket, otherwise it is a trivial solution. So, if alpha operating on a ket gives a multiple of the same ket, then we say that A n is an eigenvalue of the operator alpha, and ket A n is the corresponding eigenket. And we can have a situation that alpha ket A n is a null ket, is 0. Then if alpha is not a null operator and if ket A n is not a null ket, then this is a perfectly valid equation, and 0 is an eigenvalue. And I gave an example that if I have an say a 3 by 3 matrix, say 1 0 minus 1, the eigenvalues are 1 0 and minus 1. I just considered a simple matrix, then this operating on 0 1 0 will be 0 0 0. So, this is a well behaved, this is an eigenket of the operator this belonging to the eigenvalue 0. We said that when if alpha bar is alpha, then if alpha bar is alpha, then A n is necessarily real. Now, Dirac argues in his famous book, the reference to which I have given in my previous lecture, and he argues like this, that all observables, anything that we can measure like the position, momentum, energy, angular momentum or anything, they are to be represented by real linear operators. And when we make a measurement, a precise measurement of that observable, then we will get one of the eigenvalues. And since we will get only a real number, all eigenvalues must necessarily be real, and Dirac further argues that therefore, it's an axiom that all observables must be represented by a real linear operator. So, I repeat, Dirac writes in his book that any observable like the x coordinate of the position or the y component of the momentum or the z component of the angular momentum or the energy or something like that, any quantity that can be measured is represented by a real operator or a self adjoint operator, and when you make a measurement of that observable, you get one of the eigenvalues. We will illustrate this by solving the harmonic oscillator problem. Now, let me consider the linear harmonic oscillator problem. We had solved the Schrodinger equation for that linear harmonic oscillator problem, in which the Hamiltonian, the operator representing the total energy, is given by p square by 2 mu plus half mu omega square x square, where p is actually the x component of the momentum and x is the position coordinate, and of course, mu is the mass, omega is the natural the frequency. So, these are constants, and half is of course a constant. This is the kinetic energy and this is the potential energy. So, he says, Dirac says, since x and p, actually it is p x, but we have removed the, since it is a one dimensional problem, we will replaced by p. And he says that since x and p can be measured, these are real operators, that is x bar by definition is x, y bar is y, and p bar, that is p x bar, is p, and of course, h bar is equal to h. What we would like to do is that we would like to solve this eigenvalue equation. H, he writes it in this form, h ket h prime is equal to h prime cot h prime. Our objective for the next 1 hour or so will be to solve this eigenvalue equation. Now, the only thing that he assumes that we had derived some time back is the commutation relation. You recall that we had said that x comma p, this is known as the commutator of x and p. This was equal to x p minus p x, the two operators do not commute, and this is equal to I h cross, where h cross is the Planck's constant divided by 2 pi. So, we will just assume this and use the bracket algebra to solve this equation, and this procedure is due to Dirac himself, and it is really a very elegant procedure. Dirac defines two operators A, these are not real operators. He defines it as mu omega x, this is a constant, omega is a constant, x is of course the x coordinate, plus I p, I is square root of minus 1 divided by under root of 2 mu h cross omega. Then the adjoint of this operator is A bar is equal to mu omega x, I will be replaced by minus I, p bar is p, x bar is x, and these are of course numbers, real numbers, divided by 2 mu h cross omega. He defines these two operators and then he calculates H cross omega A bar. So, you have, if you multiply this by this, you will get 2 mu H cross omega in the denominator. The H cross omega will cancel out. So, you will get 1 over 2 mu omega x plus I p multiplied by mu omega x minus I p. Now, it is something like a plus I b and a minus I b. So, do not be in a hurry to write this as a square minus b square, because x p is not equal to p x. So, one has to be little careful. So, let us do this carefully. So, we will have 1 over 2 mu the first term will be mu square omega square x square and this I times I is minus 1, minus 1 is plus 1. So, p square and if I take minus I mu omega outside. So, it will be x times p minus p times x. This is the crucial part of the calculation. Sorry, this is p square. So, I p times minus I p is p square. So, we will have, if you write this, so we will have H cross omega, please leave some space here, A bar, this is p square by 2 mu plus half mu omega square x square. So, that is my H, this is the H, the Hamiltonian, p square by 2 mu plus half mu omega square x square. So, this is H minus I by 2, the mu cancel out omega, and x p minus p x is I h cross. So, this is I h cross. So, I times I is minus 1, minus minus plus 1. So, we will obtain this is equal to H plus half H cross omega. Similarly, I can write down H cross omega A bar A. This is equal to again H cross omega divided by 2 mu H cross omega. A bar A will be mu omega x minus I p multiplied by mu omega x plus I p. Everything will remain the same except that instead of x p minus p x, it will be p x minus I p. So, here there will be a change in sign. So, mu square omega square k x square plus p square will remain the same, except since this is in reverse order. So, this will change sign. So, I leave that as an exercise. I hope you can work this out yourself. So, we will get two equations. One is the top equation. Let me rewrite it, H cross omega A bar is equal to, leave some space, H plus half H cross omega, that is it. And the second one will be H cross omega A bar A, leave some space, is equal to H minus half h cross omega. Now, what I do is that I multiply this equation on the right by a. So, I get a here, let me write it down with a red pen, a here and a here. Here you pre-multiply by a. So, you get a h. So, the left hand sides are equal and you therefore get h a plus half h cross omega a is equal to a h minus half h cross omega a. So, I take this to that side. So, you will get h a, leave some space, is equal to a h minus h cross omega a. Operate this on the eigenket of h prime. So, a operating on h prime, h operating on h prime and this operating on h prime. We know that h prime ket h prime is an eigenket, h ket h prime is an eigenket. So, this is just a number. Ket h prime is an eigenket of the operator h belonging to the eigenvalue h. This is what we have started out, that we want to solve this eigenvalue equation. So, we say that let ket h prime be an eigenket, ket h prime be an eigenket of the operator h with h prime as the corresponding eigenvalue. So, we obtain from here, if I rewrite this slightly, so we get h operating on a h prime, that is, let me write down that as p. This will be a h operating on h prime will be h prime. H prime is a number which I can put outside. So, h prime and then minus h cross omega times ket p, where ket p is defined to be equal to a ket h prime. This is an extremely important equation, and it says that if ket h prime is an eigenket of the operator h, then ket p, which is equal to a ket h prime, is also an eigenket of the operator h belonging to the eigenvalue h prime minus h cross omega, provided this is not a null ket, because if it is a null ket, it is a trivial solution. So, I repeat, and you must understand this, that if ket h prime, of course, this is not a null ket, ket h prime is an eigenket of the operator h belonging to the eigenvalue h prime, then ket p, which is equal to a ket h prime, is also an eigenket of the same operator h corresponding to the value eigenvalue h prime minus h cross omega ket p. Now, I can proceed further. You remember that we had the relation that h A was equal to A H minus H cross omega A. We had derived this relation. Now, instead of ket H prime, I now operate this on ket P and this on ket P and this on ket P, and we will obtain H ket P is equal to H prime minus H cross omega. So, this will be equal to, please see this, H prime minus H cross omega A ket P. Let me write this as ket Q. So, this is H operating on ket Q, this will be equal to minus H cross omega ket Q, where ket Q, let me write it carefully, ket Q is defined to be equal to A ket P, and so this becomes H Q is equal to H prime minus 2 H cross omega ket Q. Thus, if ket P is a non-null ket and is an eigenket of the operator H, then ket Q, which is defined as A ket P, is also an eigenket of the operator H belonging to the eigenvalue H prime minus 2 H cross omega. Now, so therefore, we see that H prime is an eigenket. If the corresponding eigenket is H prime, then H prime minus H cross omega, the eigenket is A ket H prime, and H prime minus 2 H cross omega, then this will be A ket H prime, and similarly you can proceed indefinitely, provided any one of them H, provided any one of them does not become a null ket. Now, let me do a little more algebra. See the beauty of the algebra. Let me write down ket P is equal to A ket H prime. So, therefore, bra P is equal to H prime A bar. So, I write this down as bra P ket P scalar product. So, let me multiply this by H cross omega. So, you get H prime H cross omega A bar A H prime. Now, if you look up your notes, then we had derived A bar A, H cross omega A bar A was equal to H minus half H cross omega. So, we had derived this, that this is equal to H prime H minus half H cross omega. So, you see this is just a number, so I can take it out. H operating on H prime is a multiple of H prime. So, this becomes H prime minus half H cross omega bra H prime ket H prime. Now, you see this is of course a positive number, and see the beauty of the logic. This is of course positive definite, this is greater than or equal to 0. this is greater than or equal to 0 if and only if P is a null ket. So, this tells us that H prime must be greater than or equal to half H cross omega, and H prime is equal to half H cross omega, then this will become 0, then ket P must be a null ket. So, let me repeat this. This is a very important argument. Let me repeat this, that I have here H cross omega P is equal to H prime minus half H cross omega bra H prime ket H prime. Now, H operating on H prime is H prime. This is of course a non-null ket, otherwise it is a trivial solution. So, we assume that ket H prime is a eigenket of the operator H and the corresponding eigenvalue is H prime. So, this says that this is positive, definitely positive definite. This is greater than or equal to 0 if and only if ket P is a null ket. Therefore, this equation tells us the equation 1 tells us that H prime must be equal to or greater than, must always be greater than or equal to H. It can be H prime is equal to half H cross omega if and only if A ket H prime is a null ket. So, we see we have just now obtained that if H prime is an eigenvalue, then H prime minus H cross omega, then H prime minus 2 H cross omega, H prime minus 3 H. This cannot go on indefinitely. This cannot go on indefinitely, because then it will violate this inequality, and therefore, at some stage it must terminate, and it can terminate only if A ket H prime is a null ket, and that can happen only at a half H cross omega. Oh, this is absolutely beautiful. So, you see that you will have eigenvalues as half H cross omega, 3 half H cross omega and 5 halves H cross omega, and so on. So, if I write this as n plus half H cross omega, then n is 0 here, n is 1 here, n is 2 here, and if I write the corresponding kets as ket 0, the eigenkets ket 1, ket 2, that means what I am trying to say is that H ket 0 is equal to half H cross omega ket 0, H ket 1 is equal to 3 by 2 H cross omega ket 1, H ket 2 is equal to 5 by 2 H cross omega ket 2, and so on. We will show that it has to go indefinitely, that I have not yet proved. Then there cannot be an eigenvalue minus half H cross. For that to happen, we must have A ket 0 must be a null ket. So, we said, I go back, that if I showed that H prime is always or greater than or equal to half H cross omega. We first proved that, and H prime is equal to half H cross omega if and only if A ket H prime is a null ket. So, from half we can go to minus half, but that is not possible, and that is not possible if A ket 0 is a null ket. Okay. Let me go through this this algebra once again little differently. So, we had obtained H cross omega A bar, leave some space if you are writing, is equal to H plus half H cross omega, and then you have H cross omega A bar A is equal to H minus half H cross omega. Now, what we did was that in order to make the left hand side equal, I multiplied A here and A on the left here, A on the right here and A on the left here. Okay. So, then it became left hand sides became equal. So, now what we will do is we could have also multiplied on the left by A bar and on the right by A bar. So, if I multiply this on the left by A bar, then this is A bar, this is of course a number. So, it does not matter where I write, and on the right by A bar, H A bar this. And if I add this, so therefore, the left hand sides are equal. So, I get A bar H plus half H cross omega A bar is equal to H A bar minus half H cross omega A bar. So, what I do is I take this to this side. So, you get A bar H, leave some space here, plus H cross omega A bar, half plus half is 1, leave some space here, this is equal to H A bar. Now, what you do is that you operate this on ket H prime, which is an eigenket of the operator H. So, if you recall, H ket H prime is equal to H prime ket H prime. So, you can see H operating on H prime is H prime. So, I can, this becomes a multiple. Then I can shift it here because it is just a number. So, my left hand side becomes H prime plus H cross omega A bar ket H prime, this is equal to the same. So, let me turn the sides. So, you get H say ket R is equal to H prime plus H cross omega ket R, where ket R is equal to A bar H prime. So, we have that, please listen to the logic of the argument. If ket H prime is an eigenket of the operator H, then ket R, which is equal to A bar ket H prime, is also an eigenket of the operator H, now belonging to an eigenvalue h prime plus h cross omega. Similarly, I can then again do the same kind of algebra. Instead of operating this by ket h prime, I will operate this by ket r, and I will obtain h ket s is equal to h prime plus h cross omega plus h cross omega. So, plus 2 h cross omega ket s. So, this will be again an eigenvalue equation, provided ket s is not an eigen, not a null ket. So, if h prime is an eigenvalue, then h prime plus h cross omega is also an eigenvalue, h prime plus 2 h cross omega, provided at any stage we do not get a null ket, then it becomes a trivial solution. But I will just now show it can never become a null ket, and that the proof is as follows, that if ket r is equal to a bar ket h prime, then bra r will be equal to bra h prime a bar bar, which is a. So, if I write bra r ket r, and if I multiply this by h cross omega, then I will get h prime a bar, I am sorry, h cross omega a bar. And this was equal to, if you recollect, this was equal to h plus half h cross omega. So, h operating, if I let me just check this whether my yes, this is correct, this is correct. So, you will have that h operating on h prime is h prime, and this is just a number. So, this becomes h prime plus half h cross omega. Now, this is always greater than 0, and if this becomes a null ket, if this is 0, then h prime becomes equal to minus half h cross omega. But this violates the inequality that we had derived some time back, which says that h prime must be greater than or equal to half h cross omega. So, we had derived that h prime can at best be half h cross omega, but cannot be greater than that. But here it says that if ket r is a null ket, then h prime must be equal to this, but this is impossible. So, ket r can never be a null ket, and therefore, if ket r is never a null ket, then if h prime is an eigenvalue, h prime plus h cross omega is always an eigenvalue, is always, write down, is always an eigenvalue. So, if h prime is an eigenvalue, h prime plus h cross omega is always an eigenvalue, because ket r can never be a null ket, can never be a null ket. You will have to do this yourself once, and then it will become easy. And so, therefore, we finally obtained the remarkable result just by using operator algebra, that the eigenvalue spectrum. So, h operating on h prime, the solution of this equation is that h prime can take the values half h cross omega, 3 halves h cross omega to infinity, It cannot be terminated anywhere. So, there is an infinite number of eigenvalues. So, therefore, we write this as n plus half h cross omega, where n is equal to 0, 1, 2, 3, etc. And we label the eigenvalues. The states are therefore depend. So, you have this n is equal to 0. We represent this by ket 0. This is n is equal to 1. We represent this by the state ket 1, and then 2, which is ket 2, then 3, which is ket 3. So, if n is 3, then the eigenvalue is 7 by 2 h cross omega. This is 5 by 2 h cross omega, and 3 by 2 h cross omega, and half h cross omega. So, we get the same eigenvalue spectrum as we had obtained by solving the Schrodinger equation, and we write this down as h n. The eigenvalue equation for the linear harmonic oscillator problem is written as n plus half h cross omega ket n. So, we finally write that for the linear harmonic oscillator, the Hamiltonian is equal to p square by 2 mu plus half mu omega square x square. Then h, the eigenvalue equations are written as h ket n is equal to n plus half h cross omega ket n, where n takes the values 0, 1, 2, 3, etc. So, this represents the complete eigenvalue spectrum of the harmonic oscillator problem. Now, let me tell you, let me give you a simple example, that since ket 0 is the ground state, ket 1 is the first excited state. So, a ket 0, you see, we had said that if h ket h prime is equal to h prime ket h prime, then h operating on a ket h prime was equal to h prime minus h cross omega, a ket h prime. This was p. Now, if h prime is equal to half h cross omega, then there cannot be any state below that. So, therefore, a ket 0 must be a null ket. A ket 0 must be a null ket. Otherwise, there would be an eigenvalue minus half h cross omega, which will violate this inequality that h prime must be greater than or equal to half h cross omega. So, what was a? So, in the Schrodinger representation, therefore, a psi 0 of x is equal to 0, and let me see what it leads to. So, a was equal to mu omega a psi 0 of x is equal to mu omega x plus I p by under root of 2 mu h cross omega psi 0 of x must be 0. This is just a constant. So, you get mu omega x plus, if I write down I p as minus I h cross d by dx psi 0 of x is equal to 0. So, you write, so this is I square is minus 1, minus minus plus 1. So, you get h cross d psi 0 by dx is equal to, if you take the other side, minus mu omega x psi 0 of x. So, if I divide by psi 0, so you get 1 over psi 0 d psi 0 by dx minus mu omega by 2 h cross into x, that is it. So, if I integrate this, so you get log of psi 0 of x is equal to, if I integrate this, minus mu omega by 2 h cross x square plus a constant of integration. So, psi 0 of x, and if you recall that we had, while solving the linear harmonic oscillator problem, we had introduced a dimensionless variable xi is equal to gamma x, where gamma was equal to under root of mu omega by h cross. So, you will have log of psi 0 of x was equal to minus half xi square plus a constant. So, you will get, if you write this, this is the the ground state wave function psi 0 of x within a multiplicative constant e to the power of minus half psi square. So, using operator algebra, we have been able to find to determine. You remember that we had obtained psi n of x as n's of n h n of xi e to the power of minus half xi square. Now, for n equal to 0, so this will be n 0 h 0 of xi will be 1 e to the power of minus half psi square. So, we obtain the same wave function by using the fact that a psi 0, that since there is the half h cross omega is the lowest eigenvalue, we must have a psi 0 of x will be 0, and so therefore, we get the ground state wave function. Now, we will do a little bit more algebra, and we had said that a ket h prime is an eigenket if ket h prime is an eigenket belonging to the eigenvalue h prime, then a ket h prime is an eigenket belonging to h prime plus h cross omega, minus h cross omega, a ket h prime. So, therefore, we had written down h ket n is equal to n plus half h cross omega. So, this is my h prime. So, therefore, if I reduce minus h cross omega, so this becomes n minus half h cross omega. So, this is equal to n minus 1 plus half. So, therefore, a ket h prime or rather a ket n must be a multiple of ket n minus 1. I hope you all understand this. Ket n corresponds to the eigenvalue n plus half h cross omega, and a ket n, if it is not a null ket, then this corresponds to an eigenvalue n minus half h cross omega. So, n has been reduced to n minus 1. So, therefore, a ket n must be a multiple of n minus 1. So, let me write this down as ket p. So, therefore, bra p is equal to n a bar is equal to C n star bra n minus 1. I forgot to tell you one thing, that since these eigenkets belong to different eigenvalues, since there is only one eigenket belonging to one eigen, different eigenkets belonging to different eigenvalues must be orthogonal. M n must be 0. We had proved this, that since H is a self adjoint operator, eigenkets belonging to different eigenvalues must necessarily be orthogonal. I can always multiply each one of them such that n is 1. So, we have the orthonormality condition. So, this is the m n equal to 0 is the, for m not equal to n, this is the orthogonality condition, and this follows from the fact this follows from the fact that we have different eigenvalues, and eigenvectors corresponding to different eigenvalues must necessarily be orthogonal. We have proved that eigenvectors belonging to different eigenvalues must necessarily be orthogonal. And since you have H ket n is equal to n plus half H cross omega ket n, and you can multiply the equation by C, let us suppose some constant H times ket p is equal to n plus half H cross omega ket p, where ket p is a multiple of n. So, any multiple is also an eigenket. So, you can always choose the multiplicative constant such that bra n ket n is equal to 1. So, this is the normalization condition. This is the normalization condition, and I can put these two together to write down m n is equal to delta m n, where delta m n is equal to 0 if m is not equal to n and is equal to 1 if m is equal to n. This is known as the, as we all know, this is known as the orthonormality condition. Now, therefore, we have here that A ket n must be a, for the lower eigenvalue. So, it must be a multiple of n minus 1. So, if I denote this by ket q, let us suppose, then bra q is equal to n a bar is equal to C n star bra n minus 1. If I multiply this by H cross omega from both sides, so I get bra q H cross omega bra q ket q is equal to bra n H cross omega a bar a ket n. This is equal to H cross omega mod C n square bra n minus 1 ket n minus 1. This is equal to 1, and this is equal to H minus half H cross omega. So, from this point onwards, we will continue in our next lecture. So, we will operate this H on ket n, and we will find that that is n plus half h cross omega. So, half cancels out. So, we will left with n square, and so we will get C n is equal to square root of n. You may just try to work this out yourself, and so that when we come for our next lecture, we will go through those. Those are very extremely important relations, and they are of extreme importance not only in quantum mechanics, but in laser theory, in quantum optics, and in many other diverse areas. Thank you.